which is done from a horizontal surface, but also projection from an elevated point and the related equations, etc. Okay, so let's take it forward from that point onwards today. So we will complete projectile motion today, and most probably we'll be able to also start with the next section of kinematics, which is relative motion, but a lot of different types of questions to discuss in between. So let's start with an example of projection from an elevated point. Now this time, we will see that we are projecting it in such a way that we are giving it an oblique velocity, but with a downward component. The last class we had done an example where there was an oblique projection, but with an upward component. Okay, so let's look at this now. So at t equal to 0, we are throwing an object, the velocity, let's say like this. Okay. Which is of 25 meters per second magnitude. And the angle with respect to the horizontal is 53 degrees. Okay, so now, and this height, let us say, is 60 meters. So it will go in this kind of path. Curve slightly like this, okay. And at some time t, it impacts the ground. So what we want to do in this example is taking the value of g as 10 meters per second square. We want to first of all find out capital T, the time at which it impacts on the ground. That time is over here. You want to find the impact speed, okay, and the angle of the impact velocity with respect to the horizontal. Okay, and we want to find this distance r. Okay. And finally, we want to also find the displacement and velocity at t equal to 1 second. So just try this out with the method that we discussed in the last lecture. That in the last couple of lectures, we've discussed about projectile motion. Always divide it into horizontal and vertical component of motion, and write the individual component equations for motion along the horizontal axis, or typically the x-axis, and motion along the vertical axis or the y-axis. So just use that sort of method, and it should be quite easy to work this out. Just try this, people. I'm going to write the equations in a little bit of time, in a couple of minutes. So please try to form the equations yourself by then. Yes, Vedant, that's very good. Correct. The time is correct, which you calculated, the time of flight. So once you got that, the other things will also naturally come out to be correct if you do the calculation without a mistake. You check your answer beta again. Check your calculation part. Yeah, Jinendra, correct. Yes, you correct now. Very good. Okay, so yeah, what you have calculated is the vertical component of the velocity. Yes, Jinendra, your answer is correct. Along with that, there is a horizontal component also. Okay. Only the angle, Jinendra, will be different. It will not be 53 anymore. Okay. Because 53 was the projection velocity's angle. So you can see that that angle has changed better.
Okay, sir.
Understood now?
Yes, sir.
Okay, so let's work out the calculation, this people. So see, the first thing we need to do is define the reference frame or decide the reference frame. Now, since here the initial velocity has a vertically downward component, it's a good idea to take the y-axis downwards. Okay. You can take it upwards, but unnecessarily you'll be putting a minus sign to both the things, the initial uy as well as the acceleration along the y-axis. So it's much better that we, from the beginning, make things simple and keep the y-axis downwards because the object goes down from the beginning. Okay. Straight away having a downward motion like this. So the first thing you have to do is express the initial velocity in component form, okay, for the given coordinate system. So 25 meters per second at an angle like this of 53 degrees at t equal to 0. So that initial velocity in component form I will now write as u cos theta I cap plus u sin theta. Why plus? Because I've taken y-axis downward. So this is the downward component. Okay. So you can see that the x component, which is u cos theta, will be 15 meters per second, and it's in this sort of direction. And the y component, which is u sin theta, will be 20 meters per second, and that's in this sort of direction. Okay. Then, of course, as it falls, it throughout has an acceleration g downwards. So the acceleration vector will be written as plus gj cap because it's downwards. So the acceleration's x component is 0. The acceleration's y component is 10 meters per second square downwards. Okay, so now we can see that at some time t, the velocity's horizontal component will remain ux, which is 15 meters per second. The velocity's vertical component will become uy plus ayt. So that will become 20 plus 10t as a function of time. Whereas similarly, the x component of displacement will be 15t, whereas the y component of displacement will be, so become 20t plus 5t square. In meters, this is in meters per second. Okay. So these are the equations that we need to solve. Yes, that's correct. Okay. You can write the angle like that, or you can also just write it in tan inverse form. It will be a little easier.
Yes, sir.
Cos inverse is also fine. Okay,
But like, sir, then y component के साथ we have to equate it, then we have to divide, right?
Right. Okay.
Okay.
So at the time when it impacts the ground, t equal to capital T. So the first part you can see that at t equal to capital T, the y component should be how much? H of displacement. Should be this h, which is 60 meters. So from this equation, we'll see that $60 is equal to 20 capital T plus 5t square. So solving this equation now will give me the value of time. T square plus 4t minus 12 is equal to 0. You see that so we get two roots, minus 6, which is not acceptable. It's a time cannot be negative, and 2, which is the correct one. Okay. So capital T will be 2 seconds. Now, once we have got that, we can see that at t equal to capital T, the velocity is the impact velocity. So Vx is 15, but Vy is 20 plus 10 into 2 or 40. So the impact velocity becomes 15 I cap plus 40 j cap. So if the impact velocity is making this kind of an angle with the horizontal, this angle is phi. So in that diagram, you can see that at velocity, this angle I'm taking as phi, and the impact velocity is horizontal component is 15, whereas the vertical component is 40. So you can see two things here. That one is that the magnitude of the impact velocity or the speed is much. So 5√73 meters per second, and the angle phi will become tan inverse of 40 by 15 or tan inverse of 8 by 3 or tan inverse of 2.67. So these are the answers we are looking for. We can use a calculator to find this in degrees now, tan inverse of 2.67, but that is not required. We can give the answer this way. So this becomes the answer to all these different parts. Okay. Now the other thing, you want to find the displacement and velocity at 1 second. So for that you have to just substitute in these above equations. Okay. So ultimately everything is coming from the component equations of motion, as is always the case in anything to do with projectile motion. Okay. Hardly ever things are complicated in that sense. Okay.
Sir,
Yes.
the range would be 30, right?
Range भी निकालना है अपने को. So range will be 15 into 2. That's correct. 30. The horizontal displacement, okay, will be the value of the x coordinate at time 2 seconds. Okay, or capital T. So that's correct. That will come out to be 15 into capital T. At t equal to capital T, the value of x is equal to r. So therefore, that's 30 meters. And then fourth part, you can see that at t equal to 1 second, the x coordinate would have become 15 meters. The y coordinate would have become the y coordinate as a function of time, you can see here, is 20t plus 5t square. So it will become 25 meters. And therefore the displacement would be 15 I cap plus 25 j cap in meters. So it's coming from these two equations. That equation. And the velocity have an x component of 15. but a y component of 20 plus 10t would be 30. So the velocity vector at t equal to 1 second would be 15 I cap plus 30 j cap. So this is the velocity and this is the displacement at the time of 1 second. Okay, people, so hope all the parts of this question are clear. We'll do one more example of this type of question of projection from an elevated point. And then we will move on from there to the next part, which will be projection from an inclined plane or projectile motion on an inclined plane. Okay, so before we do that, another example. So now we have this situation. We have, let's say, two buildings which are adjacent to each other. And this one is at a height of 55 meters on the ground, and this one of a height of 100 meters. And also the distance between these two buildings that is 60 meters. Okay. Now we want to project an object horizontally from this point. what should be the minimum projection velocity so that it lands on this other building instead of landing on the ground below. You have to give it some minimum value of the projection velocity so that it lands on this building.
So horizontal projection.
Yes. Okay. An example of the first part is an example of horizontal projection. So find the minimum horizontal projection velocity u needed so that the projectile lands on the second building. And second part, now for the second part, the width of this building is given to us. The width of this building is, let us say, 40 meters. So the maximum value of u horizontal so that the projectile lands on building B. Take the value of G as 10 meters per second square again. So this part of the question should be fairly easy. Just try this out. Yes, very good. Number of you have got the answer correct. Vedant, Soham, Jitesh. The minimum value of initial velocity is correct, which you have got. The answer should be 20 meters per second for this part. The minimum should be 20 meters per second. And correct. The maximum is also correct for you, Soham.
So even I said it.
Yeah. Just checking. Jinendra, Vedant, Soham, Jitesh. Yes, all your answers are correct. Okay, so U maximum will come out to be 100 by 3 or 33.33 meters per second.
Sir, the second part can be found by like from the first one on, like it's
Yeah,
visual.
I mean, basically what you have to understand is that if you have a general sort of landing like this over here, okay, then first thing you can see over here that the time at which you land, that is independent of what the U is.
Yes, sir.
Because the U is only horizontal. So again, you take this as your y-axis and this as your x-axis. So in general, you will see that x is ut, but y is half gt square. So that is 5t square. Okay. So if it lands on B, okay, then y should be equal to h2 minus h1. Should be this distance from here to here, which is h2 minus h1, which is 45 meters at t equal to capital T. So from this equation, you can see that 45 should be equal to 5t square. So t should be equal to 3 seconds. Now, once you know it's 3 seconds, now for it to land on B, basically you can see that this range kind of thing from here to here, this R should be greater than 40, greater than equal to will also do, and less than equal to, sorry, 60, my mistake. D is 60. So it should be greater than equal to 60 so that it does not do this. We don't want this situation. We don't want this. Okay. And similarly, we don't want this kind of situation also. What we want is this kind of situation. So for that kind of situation to occur, we want that at that time capital T, the horizontal displacement should be greater than capital T but less than D plus W. Okay. So it should be greater than 60 but less than 100. So from that only we'll get this. So from this you can see that Qt should be greater than equal to D but less than equal to D plus W. So U is unknown, but the time we have calculated from above is 3 seconds. So U into 3 should be, so that's how we get that U should be greater than equal to 20 meters per second. And at the same time, it should not exceed 33.3 meters per second. Okay. So this kind of situation becomes pretty common at JEE level for application of projectile motion.
Sir, just like just extra thing. When we take this is normal case when the ball doesn't bounces. If it bounces, then we have to take components and then Newton's laws of motion say like third law.
In the case of bouncing, here see what we are solving now, it doesn't matter whether it bounces or not because we are only solving up to capital T.
Yes, sir.
Now, when the bounce will affect, when we are considering what is happening after it impacts. Okay. So to consider after it impacts, we have to consider something called collision theory. You might have heard the terms like elastic collision, inelastic collisions. You ever heard these type of terms?
Yes, sir. Like we have experience to.
Yes. You know? So rather than Newton's laws, they will be applying the concepts of impulse and momentum. Okay. Because in a collision, what happens? The time of impact is very short, but a very large amount of force acts during that time. You understanding the point? No?
Yes, sir.
Like, is there difference between like pushing an object continuously versus like if you just give it an initial push, like an initial impulse? No, like there's a box lying on the ground. One thing is that you're, as a person, you might be pushing it continuously with some constant force. That's one situation. So it'll have a uniform acceleration for the entire duration of time for which you're applying the force. But another situation is that you might just kick that object. So when you're kicking that object, your foot is in contact with it for a very short duration of time. But during that short duration, the force is very large. So it applies what we call an impulse, which is force into time. And that impulse is equal to the change in momentum. That is something called impulse momentum theorem, which we will study in a slightly later chapter after Newton's law. Okay.
Okay, sir. So
So
that
that
will have calculus application because there is short time now.
something like that, calculus application. So here, for example, when that ball or something comes and bounces against the surface of B, what will happen is B will apply a normal reaction, but that will not be a normal reaction like mg. It will be much larger because an impact is happening. And the duration of the time for which that normal reaction kind of force will be acting will be a very short amount of time. It might be a microsecond or something like that. So that kind of force is called a collision impulse force. It is not called a normal force or a normal reaction force. It's actually called a collision impulse force because it has that special feature that it acts for a very short duration, but at the same time it has a very large magnitude.
Okay, sir.
That's one thing. Now the other thing is how much the ball will jump. Okay, so for example, here when the object is impacting B, you can see what will be the vertical component of velocity. It will be gt now, and the time is 3 seconds.
Yes,
So
sir.
it will impact B with a downward vertical component of how much? 30 meters per second. Okay. Now after the impact, how high it bounces, that depends on what will be the vertical velocity after impact. No?
Yes, sir.
So how much that will be, that depends on the material of the ball. If it is made of elastic material, highly elastic material, like a tennis ball or a rubber ball, then it will bounce higher. Because what happens is that it is able to extract more contact force from that surface. Okay. Whereas if it is made of inelastic material, like most inelastic material you can think of is like chewing gum, it just sticks to the surface.
Yes,
So
sir.
in that case, it does not bounce. Okay, so that's where the concept of elastic versus inelastic collisions comes in, and again we'll be studying more about that. Okay.
Okay, sir. And even like if something wooden, something which is very rigid and like very compact thing.
Yeah, so it will have comparatively very less amount of bounce.
Yes.
No?
Yes,
It might
sir.
not even bounce, it might just slide along. It
Yeah.
depends on the surface. Okay, so now we move on to the next part of projectile motion, which is projection from an inclined surface, or projectile motion with respect to an inclined plane. This is the last part of projectile motion, theory wise. So this is something that is not there as a separate theory portion in HC Verma, but you will find it in our module notes.
It is there in NCRT also.
Yeah, you will find it in NCRT or Resnick Halliday for that matter. Okay. So projection on an inclined plane can be, again, two situations. You can be projecting it up an inclined plane or down an inclined plane. So we'll discuss both the situations. Okay. But first of all, let us say we have an inclined plane which is having an angle with respect to the horizontal of alpha. Okay. Now in the first case, let's take a situation where we are projecting a particle from somewhere on the lower side of the inclined plane, okay, such that we expect to make it land somewhere higher up on the inclined plane. So the projection velocity at time t equal to 0 is u. And now what we'll do is, instead of giving the angle of projection with respect to the horizontal, it is given with respect to the inclined plane. So what will happen is this particle will take a path like this. Now the path is just the same as it would have been if you had projected it from a horizontal surface. But the difference is it does not come back to the same horizontal level. In fact, somewhere in between, it impacts the inclined surface again at, let's say, some time capital T with some impact velocity, let's say vi. So we want to find out all this. Okay. So here alpha is the angle of the inclined plane with respect to the horizontal. and beta is the angle of the projection velocity with respect to the inclined plane. So actually, with respect to the horizontal, it's making an angle of alpha plus beta. So again, if it lands at a point which is at a final displacement of r where it lands, okay, and if it also during the course of its motion, if it makes a situation where the maximum distance it reaches from the inclined plane is this d max. Now we want to calculate all these things. We want to find the time of impact or the total time of flight, you can say. We want to find the range on the inclined plane, not the horizontal range. So we can't use the horizontal range formula anymore. We also want to find this, which is the maximum distance from the inclined surface, not from the ground below. During this projectile motion. Okay. So what we do here is to solve this. Now, the other thing to understand is that from t equal to 0 to t, the acceleration of the projectile is how much? It is g only. Okay. It is still motion under gravity. So that thing hasn't changed. Okay. The only thing that is changed is that instead of going and hitting a horizontal surface at the same level from which we had projected, or at a level below from where we had projected, whatever be the case, okay. Instead of that, it's now going and hitting that inclined surface from which we have projected. Rest, nothing has changed. Okay, so it's motion under gravity. So what we do here is that the choice of reference frame is slightly different, or the coordinate frame. What we do is, because we are solving with respect to the inclined plane. So just like you have done in Newton's laws of motion, whenever you're solving a free body diagram on an inclined surface, okay, then what you do, you take the axis parallel to the inclined surface and perpendicular. Instead of vertical and horizontal, you take x-axis and y-axis along the inclined surface and perpendicular to it. The same thing we'll do over here. We'll take the origin of our coordinate frame at the point of projection. And in this case, because it's going up the inclined plane, we can take the x-axis up the incline surface, and the y-axis normal or perpendicular to the surface. So what I want you to do is make the reference frame diagram and then resolve the initial velocity and the acceleration, both things, and show it in component form. Okay. So next thing what I want you to do is, with this choice of reference frame, you have to express these two things, u and a, in component form. Just try this out, people. We'll discuss. No, so Jitesh, see, the thing you have to understand here, na, the axes have changed. So all your resolution of the vectors will change. Okay, so we cannot use any of the standard formulae that we have seen earlier in projectile motion, because that is with respect to horizontal and vertical. Na? You're understanding the point, beta?
Yes, sir. Like, sir, my time of flight is coming something like 2u sine theta upon g cos theta.
G cos alpha, correct.
Yeah, that one.
Numerator will have a sine beta, 2u sine beta, and
Sine beta.
denominator will have a G cos alpha, correct?
Yeah.
Should be getting that. Okay, good. Okay. So with respect to this angle is alpha. Okay. Just a moment, people. Okay, so the first thing is that, as we have discussed, we will take our coordinate frame like this, that our x-axis is along the inclined plane going up like this, and the y-axis is perpendicular to the inclined plane, like this. And now origin is the point of projection. So what will happen is our u will be expressed as u cos beta I cap plus u sin beta j cap. But again, as the projectile is in flight, at any point of time, what is the acceleration? It's always g. At any point of time, the acceleration is always vertically downwards. So the acceleration vector, if you look at it, that one, how it is oriented, it's like this. It's a vertically downward pointing vector. And with respect to our coordinate frame, therefore, it looks something like this. Our x-axis is along this sort of direction, and our y-axis is along this sort of direction.
Yes.
Like you're used to doing for Newton's laws, you'll see that if the inclined plane is making an angle alpha, then G is making an angle alpha with the vertical. Okay. So G's vertical component will have a negative sign, and it will be G cos alpha. And G's horizontal component will also have, not vertical actually, the x component will also be along the negative x-axis, and it will be G sin alpha. So the acceleration will be minus G sin alpha I cap and minus G cos alpha j. So if we write this in component form, we can see that ux is u cos beta and ax is minus G sin alpha. And similarly, uy is u sin beta, but ay, unlike in that case where it was horizontal and vertical, is not minus G, it is minus G cos alpha. So now both of these are accelerated motions. Both of these are ones having uniform acceleration, and in this case, both are having negative values. So from this, we can see that therefore, at some time t, the projectile is here, the velocity v like this, and position xy, we can see that at t equal to t, dx will be u cos beta minus g sin alpha t, and dy will be sin beta minus g cos alpha t. And from this, the velocity vector is, and x coordinate will be u cos beta t minus half g sin alpha t square, and y coordinate will be u sin beta t minus half g cos alpha t square. And from that, you can see that when it lands on this over here somewhere at t equal to capital T, everything will come from these two equations. So now you can see that at t equal to capital T, the y coordinate should become 0. So therefore, from equation 2 that I've written there, sine beta t minus half g cos alpha t square should be 0. So we have factorize it and you get this kind of, so exactly same method, okay, but only difference is now the acceleration has a component cos alpha instead of just being g along the y-axis. So time of flight will come out to be 2u sine beta divided by g cos alpha. Now if you write it in parametric form, you can see that it's very similar to what we had got earlier. It is 2uy divided by magnitude of ay. Only difference is in a normal situation, uy is u sine theta and ay is minus g. Here ay is minus g cos alpha. So that's the difference. Okay. Parametrically, it's the same. For example, this is how we calculate the time of flight. Now, similarly, we'll see how to calculate the maximum distance from the inclined plane, d max, and also the inclined range or the range along the inclined surface, which is r.
So all types of projectile motions are mirrored, right?
Sorry, what?
Are like mirrored, means the half.
Have a symmetry.
Yeah, they have a symmetry.
Okay, so you'll understand one thing here, that when you look at when it reaches the maximum distance point, there is a symmetry in terms of time, but there isn't a symmetry in terms of x coordinate here, which you can kind of by diagram also. No? You can see because the x component of velocity is decreasing. So you can see this line that I've drawn parallel to the y-axis, now where it's reaching the maximum distance point. This is not cutting it in half and half in terms of the x coordinate. But what we will see is that when it reaches here, there are two things that happen. The velocity becomes parallel to the x-axis. It just becomes vx I cap. The y component of velocity is 0. And the time is half the total time of flight. Okay. So that we will be able to analyze from these two equations again. Okay. So before we come to that, so this formula is clear now. Okay. Now the next thing is that we want to calculate the maximum distance. Okay. So basically, again, y is the distance from the inclined plane. So d max is nothing but maxima of y. So if you look at this function y as a function of time, you realize that it's a quadratic function like this again. Okay. So how does the y coordinate look like as a function of time? Graphically speaking, it looks like this. The y coordinate is 0 at t equal to 0. It increases to that maximum distance at some particular time. And then again it decreases and comes to 0 at capital T. So you can see that y is equal to 0 at t equal to 0 and t equal to capital T, which we saw is 2u sine beta divided by g cos alpha. So this also shows that it's a quadratic relation. The graph is a parabola. The parabolic curve. So parabolic curve has this symmetry property. So the time over here should be t by 2. So because it's this, the time over here should be capital T by 2. So you can see that y reaches its maxima at t equal to capital T by 2, which is u sine beta divided by g cos alpha. So therefore, this maximum distance from the inclined plane is nothing but the y coordinate, but at what time? T by 2. So it's going to be u sine beta into t by 2 minus half g cos alpha into t by 2 whole square. Now we'll substitute the value of t by 2 from above. So that will give us the value of the maximum distance. So it is u sine beta into t by 2, which is u sine beta divided by g cos alpha. So this just looks lengthy, but once we solve it, you'll see it's quite straightforward. U sine beta divided by g cos alpha whole square. So now in this expression, if you take u square sine square beta common, and you take in the denominator g cos alpha common, again you'll have 1 minus half. So you get a very similar type of formula. Okay, of course, it involves two angles, alpha and beta, but if you write it in terms of parametrically, you will see it's very similar to what we'd seen before. It is uy squared divided by 2 times magnitude of ay. Only in the regular case that magnitude of ay is g, and the numerator uy is u sine theta. Here it is u sine beta, and the denominator, instead of ay being equal to g in magnitude, it is g cos alpha. So this is this thing, this is the formula for
Max height.
maximum distance here from the inclined plane. So just make a note of this, people.
Yes.
Okay, so one more thing we should just additionally note down over here, that at the instant when y is equal to d max, the time is t by 2, which we've already seen, and py is 0. You can check earlier that we had the equation that py is equal to u sine beta minus g cos alpha t. So in this, if you substitute t as p by 2, which is u sine beta divided by g cos alpha, you'll get vy as 0. So which basically means that the velocity is along the x-axis or parallel to the inclined plane at that moment. Okay, so when it reaches that maximum distance point, that is somewhere over here, so the velocity at that moment is like this. It's parallel to the inclined plane, and the time is half the time of light. And but also keep in mind that x coordinate is not equal to r by 2. Which you can also justify from this equation, that x was u cos beta t minus half g sine alpha t square. So because there is this second term, x is no longer linear. X is not directly proportional to time. So at half time, the value of x will not be half the range. This is just another property to keep in mind.
Yes, sir.
Okay. And now we come to calculation of the range. So the thing is that don't try and memorize these formulae. It gets too much. Just understand how these quantities are derived conceptually. They're all derived from the 4 equations: vx, vy, and x and y coordinates as functions of time. So whenever you're doing a question with respect to the inclined plane, don't try to make it formula based. What you do is you take your axis x and y according to the question given, and you resolve all your vectors, that is the initial velocity u and the acceleration g, and you write those equations. And from those equations, you'll be able to see the answers. The moment you write the equations, write them numerically. Don't write them as u cos alpha and all that. Just substitute the value of u alpha and all that. So you get those equations numerically. So from those numerical equations itself, you'll be able to derive the values of capital T, D max, range, and all that numerically. So it will not be a hassle. Okay. However, here we will do it parametrically. Yeah, exactly, Jitesh. Only the angles. But yeah, what is also different is that in this case, AX is not 0.
Yeah.
Because so that's what makes it a little bit different from the standard case. Okay, rest the method is the same of deriving. So just keep the method in mind. Just practice 3-4 questions, that will be more than enough. So that will be doing in class itself. So anyway, let's see how to calculate the range. So at t equal to capital T, the value of x is r. Okay. So therefore, from equation 1, which we had written earlier, that x is u cos beta t minus half g sine alpha t square, r should be equal to u cos beta capital T minus half g sine alpha t square. So in a numerical question, actually, you should now derive the answer from this formula that we written. Okay, because you've calculated capital T above. So just substitute those values. You don't need to write it parametrically like I'm going to do next. But anyhow, we will, for this derivation here, I'll just write the whole thing. So capital T was how much? It was 2u sine beta divided by g cos alpha. So you'll see this becomes a very lengthy term, but at the same time, it does get simplified after a bit of effort. So that effort is something like this. You will have to take u square. In fact, take 2u square by g common. So you see that the first term will give you cos beta sine beta divided by cos alpha. And the second term will give you sine alpha sine square beta sine alpha into sine square beta divided by cos square alpha. So now you take some more terms common. So what you do here is take also sine beta you take common, and you take LCM in the denominator of cos square alpha and take that common. So that sine beta has gone out. You've taken cos square alpha from the denominator. So numerator you'll be left with cos alpha cos beta. And from the second term you've taken sine beta by cos square alpha common. So you have sine alpha sine beta. This nicely fits into a formula that is cos alpha plus beta. So in a sense you get a formula, but what I'm saying is don't need to put extra pressure on yourself to memorize all these formulae, because it's very easy to get confused then. It's better to just understand the method by which you have derived this, okay? And then just use that method directly. So I'll show you in a numerical problem also how we'll do it. We'll not get into all this complicated thing. What we'll do is we'll resolve the vectors in the beginning only, and we'll write our ux, uy, ax, and ay in numerical form in meters per second and meters. And from there, it will just become very simple.
Sir,
Somebody had a question?
sir, what is written there in second wala R ka bracket? C alpha beta sin beta.
Which one?
That
Like
second.
second.
From below it is third in bracket.
Okay. So see what I've done is now I've taken 2u square by g common. Okay.
Yeah.
So see what is the first term? It was 2u square by g into cos beta sine beta divided by cos alpha.
Yes, sir. Got it. Yeah,
Okay.
got it.
And the
Yes.
second one also, just do that algebra. There's 2u square, but there's half outside also, no? So you can take 2u square
Sir.
by g common. You know?
Yes, sir.
Then next step, what I've taken is I've done LCM. I've done two steps in one actually. First, I've taken LCM inside the bracket of cos square alpha, LCM of the denominator, and then
Okay.
I've taken those things common. Okay, so just be careful when you're doing those steps. Okay, people. So hope this whole algebra part here was clear. Okay, just a little tricky taking all those things common and all. But we'll see that when we actually do numerical problems, we don't get into all this formula and all. So basically now we'll do an example where we cover both the cases. The one where we are projecting from below the inclined plane, I mean from somewhere below and it's going and hitting somewhere at the top, as well as the second case where we are actually projecting from somewhere above, but such that it's going down the incline. Okay, so let's see both these cases within one numerical problem. So this is part one of the example, this is part two of the example. So in both the cases, we'll take these values the same. This alpha is 45 degrees. Again, alpha here is 45 degrees. But in this case, we are projecting like this at a speed of 35 meters per second at an angle beta of 37 degrees like this. In the second case, we are projecting somewhere like this. Again, where this angle is 37 and the speed of projection is 35 meters per second. We'll take G as 10 in both the cases. So we have to calculate all those standard things. Okay, in each of these cases, calculate the range, the maximum distance from the inclined plane, and the time at which it impacts. And we'll also calculate the impact speed. There's something new we'll do over here. So take G equal to 10 meters per second square. Take root 2 as its approximate value 1.4. Okay, and find all these things: time, range, maximum distance, and the impact speed in both cases. So as I said, don't need to get into all those formulae parametrically. It's way too lengthy and unnecessary. From the beginning only, you do those steps that you first take your x and y axis properly and resolve u and a or u and g such that you have numerical values of ux, uy, and ax and ey, so that you can form the equations with numerical values. And then you'll see it's quite easy to solve this case. Okay, very good. Jineend, Jitesh, and Soham, all three of your answers are correct. Okay. So I'm just going to put up the methods for each of the parts. You just continue with whatever you're doing. Those of you who have finished the first part, you can continue working on the second part and later just verify the answers. Okay. So I'm taking X and Y axis like this in the first part. You can see that with respect to the horizontal and vertical, this angle is 45 degrees. Okay. And my initial velocity vector from where I projected is something like this. This will be 37 degrees. Yes, Vedant, that's correct. Very good. Okay. So I will get to write my initial velocity as u cos 37 I cap plus u sin 37 j cap. So from this, I'll write ux as 35 into 4 by 5. That's 28. And uy as 21 meters per second. Okay. I'll write my a as minus g cos 45 I cap minus g sin 45 j cap. Because it's 45, doesn't matter which one we are taking, cos and sin. So more importantly, we'll get ax as a, which I can write as or minus 5 root 2, that is minus 7 meters per second square, because I've been asked to take root 2's value as 1.4. The instruction in the question is given. This is also minus 7. So now you can see that everything becomes very simple. Vx is going to be 28 minus 70 and Vy is going to be 21 minus 70. Okay. X as a function of time will therefore become 28t minus 7 by 2 t square. Y as a function of time is going to be 21t minus 7 by 2 t square. So once you got these set of equations, everything becomes very simple, as you can see. Okay. So at t equal to capital T, y should be 0. So capital T will become 21 divided by 7 by 2. So capital T should become 6 seconds. And X should become equal to R. So range will become 28 into 6 minus 7 by 2 into 6 square. Let's see where that leaves us. Okay. So 28 into 6 minus 21 into 6. 7 into 18. So that's the same thing as 21 into 6. So we can take 6 common. So I should get the range as 42 meters. So you can see that we could have also used all those formulae, but it was really unnecessary because just remembering the formula is a pain actually. So it's much better to just write it this way. Okay. If you've gone by the formula method, it is like 2u sine beta divided by g cos alpha. So it is 2 into 35 into 3 by 5 divided by 10 into 1 by root 2. So it is 7 into 3 by 10 into 1.4. So this is the formula based method. Okay.
So that comes out as 5.88. So then we can round it off as 6.
But then what you have taken root 2 as? Have you taken it as 1.41 or something? If you take it as 1.4, it will come exact better.
Okay.
It should come exact. And now from this equation, you can see that D max is equal to Y's maxima. So Y is again 21T minus 7 by 2 T square. So you can see that Y as a function of time, varying like this, that this is 6 seconds, this is 0. So it will reach maximum value at 3 seconds. So D maximum is the value of Y at T equal to 3 seconds. So this is what I'm getting D maximum is. Check the answer. Okay, so Caleb, this is clear now with the formula method also?
Yes, sir. Got it.
Okay. Okay. So people will conclude this session today here, but what I want you to do is just add this second part to your homework. Okay. We'll discuss it in the next lecture. The second part here added to the homework. I've already sent you a worksheet also in projectile motion. So by next lecture, make sure you go through all the questions and try them out from the worksheet. Also in HC Verma, you have to do up to question number 45. Yeah, I'm showing the last part. Okay, so you can just note down in HC Verma, do all questions up to question 45 of kinematics. After 45, there is relative motion. So those things we'll be discussing in the next lecture. In the main exercise, do questions 1 to 45. Many of them you would have done in straight line motion. Okay. So probably you would have done up to 22 or 23, something like that in your straight line motion part. Now you can continue from that part and two-dimensional motion and projectile motion. You'll find few questions are there which are tricky, like question 44 and then few around 35, etc. also. But mostly you should be able to negotiate the questions. We'll discuss the doubts of all this in the next lecture. Okay. Only on completion of the doubts of projectile motion, we'll move ahead with relative motion after that, which is the last portion of kinematics. Okay. So that's it for today's session, people. Wish you all the best. Thanks for attending. Have a nice day.
Bye.
Bye.
Bye, sir. Thank you, sir.
Bye, sir. Thanks.
Bye.